Hello everyone again. This is the same problem uh, with the inductor in the circuit, the LR transient circuit, right? But this time I'm going to solve this problem using Thevenin's equivalent circuit method, right? You can solve the same transient problem with either differential equation approach or using Thevenin's equivalent circuit. So let's do that. So using Thevenin's equivalent circuit, what you have to do is first you have to convert this circuit into Thevenin's equivalent circuit. So Thevenin's theorem says any complex network circuit can be reduced to just a single source, right? Single voltage source, right? With a series resistor, right? And then now you put this inductor as your load. Your inductor is your load now. So this is the basic idea. So this is your VTH and this is your RT. That's what you first need to find. So you first need to find for this given circuit with the load removed, which is load your inductor. You first need to find out what is the equivalent Thevenin's voltage and what is the equivalent Thevenin's resistance. And then you put the inductor as a load, and then it starts, the voltage across the inductor starts increasing, right? It's a charge, kind of charging, increases exponential over time, and then you can find out voltage across the inductor and current through the inductor, right? And what is the time constant? So time constant will be just the L over RTH, right? Just like in capacitor is just the R times C. If you have inductor, is the time constant is the inductance divided by the equivalent Thevenin's resistance, right? And then the I of L is just VTH over RTH, right? I max, right? So I max will be, So you can say the maximum current through the inductor, right, will be the Thevenin's voltage divided by Thevenin resistance. So let's do that. So this is the main idea, right? So first your job is to find out the equivalent Thevenin's resistance, right? So then now remember how to do the Thevenin's equivalent. So you have to, so load is removed. So the inductor is already removed here, right? Before you close the switch. And then this equivalent circuit will be something like that. Right? You have to turn off the sources. You have only voltage source, so turn off means you have to short circuit the voltage source. And you have now this resistor, right? And you are finding the resistance on this arm, right? So whatever resistance you look at here at this terminal is your Thevenin's equivalent resistance. So you just turn off the voltage. This is your 20 kilo ohm, and this is your 4 kilo ohm, and this is your 16 kilo ohm. So this, on this branch, this is in series, right? So basically, yeah, now you have 20 kilo ohm and 20 kilo ohm, right? In parallel, basically. That's it. So that's your RTH. So 20 kilo ohm, right? And 20 kilo ohm. So your RTH, so the Thevenin's equivalent resistance is 10 kilo ohm. That's it, right? That's your Thevenin's equivalent resistance, right? Now let's find the Thevenin's voltage. So what is Thevenin's voltage? So Thevenin's voltage is with the load removed, right? So with the load removed, with the inductor removed, inductor is your load. With the inductor removed, so you have now voltage source 12 volts. This with the load removed is already removed, right? And here this is actually 20 kilo ohm. So whatever voltage you see from this end at the end is your Thevenin's voltage, right? With the load removed is 20 kilo ohm. So basically it's a voltage divider, right? So this voltage will be divided So whatever voltage you see here, right, is your Thevenin's voltage, VTH. And this is the voltage, right, across 20 kilo ohm, and it will be divided equally. So VTH is 20 kilo ohm, which is R2, right, divided by 20 plus 20, 40 kilo ohm, times 12 volts is 6 volt, right? It will be. So 6 volts is your Thevenin's equivalent voltage. Now we found the Thevenin's equivalent voltage, and we also found the Thevenin's equivalent resistance. Now your circuit becomes very simple after that, right? So after that, your circuit simply becomes this. Once you find the equivalent voltage and resistance, the Thevenin's equivalent circuit becomes this. So this, your Thevenin's, we just Thevenin's equivalent circuit will be like this. Have a single voltage source, which is Thevenin's voltage, VTH, right, in series with a Thevenin's equivalent resistance, right? This is your VTH, which is 6 volts, and then this is the output, and then you put the load, and your load is what? Inductor. Your inductor is your load, which is 80 millihenry, right, based on the question. And then you can find out this load current, right, which is the inductor current, and what is the inductor voltage, right? And so let's find that out. So your VL, so first of all, what is the time constant? Let's first find the time constant. The time constant of the given circuit is, because it's a LR circuit, so L over RTH. So L is 80 millihenry, and RTH is RTH was 10 kilo ohm, right? 10,000. So tau is 8 microsecond, and which is what we found from differential equation, right, approach. Okay, you got the time constant. Now we know how voltage. So in inductor, voltage decreases, right, over time. It's exponential decreases over time, like that, right? And then you can directly write down. But you need to know the initial voltage, right? At t is equal to 0, right? What was the voltage across the inductor, right, at t? And then you have to do this here, which is the voltage across the second 20 kilo ohm, which was 6 volts, right? And you can just, so just before you close the switch, what was the voltage across the inductor, right? And you can immediately write down this equation like that, and on the right hand side I have combined. This is 20 kilo, 4 plus 16 kilo ohm, 20 kilo ohm. This is also 20 kilo ohm. So whatever you're looking here is VL, right? So this is 12 volts. So VL was 6 volts at t is 0, and that will decay now. So your general equation is V of LT is V naught maximum E negative t over tau, right? So it's a 6 minus t over 8 microsecond, right? And this is how the voltage across the inductor decay over time, right? So however, current increases exponential over time, right? So how do you do that? And so now current, how does the current changes? So current increases. We know in inductor, current slowly increases, right? Current, if you measure the current across the inductor as a function of time, it will go like that, right? And the exponential increase, right? The decay, this is the decaying exponent, is explained by this, right? So it's some unit, some I max, maximum current in the circuit, 1 minus E minus t over tau. The time constant remains the same, but where I max is just VTH over RTH, right? That has to be the maximum saturated voltage, right? Which is this, which is I max, right? Eventually, so once the current becomes maximum, the inductor simply works as a closed circuit. Inductor doesn't have any resistance, right? So inductor simply works as a closed circuit. So this should be the maximum current, which is in this circuit, right? This is the maximum current because inductor will have zero impedance, right, at maximum. Okay, so VTH was 6 volts and RTH was 10 kilo ohm, 10,000, right? So your Imax is so your Imax is 0.6 milliamp or 10 to the power minus 3 amp, right? And then your function, the current function is so 0.6, I'm going to say milliamp, right? Let's keep it in amp. And 1 minus E minus T over, what was the time constant was, time constant was 8 microsecond, right? And this is measured in amps. So this is how the current changes, right, as a function of time. And that exactly matches with the results from our differential equation method, right? So you can, any transient problem, transient circuit, charging and discharging circuit can be solved using either differential equation or using Thevenin's equivalent circuit, right? But however, remember that in some complex circuit problem, you won't be able to solve the transient problem using Thevenin's equivalent circuit, especially if you have a current sources, something like that.